Hey everyone, welcome back to Chem class. We are continuing our intermolecular bonding lesson. As a reminder, there are three categories of bonds: covalent, ionic, and metallic. We are still working on covalent bonding today. We are focusing on actually double and triple covalent bonds. Okay. The goal of bonding, as mentioned earlier, is to attain stability, okay? But the vast majority of elements' goal is to form an octet, and that is to achieve stability like the noble gases. Now, small atoms like hydrogen only need 2 electrons. Now, today I will be referencing additional reference tables, that is table P and table Q. This was part of the homework last week, table P, table Q, so please be aware that I will be referencing that eventually in this lesson. Okay, so let's start with double bonds. Now, double bonds, my first example is the diatomic oxygen. A double bond is going to have 4 electrons shared, and this is actually the ball and stick model for oxygen, okay? And there's our double bond. Okay, so to draw this, I'm gonna first show you, by the way, you should always use pencil when you're drawing, so I hope I don't mess up. I've got a lot of pressure here. I'm using ink, okay? But let me just show you the Lewis structure for oxygen. We know when we look on the periodic table that oxygen has 6 valence electrons, okay? So there's my 1 Lewis structure for oxygen. I'm going to draw another oxygen because I do want this to be a diatomic oxygen, right? So let me kind of draw this way. Now, this is problematic. This is not going to work. But to show the bonding between oxygen, it is not accurate. And let's look carefully at that. We have 2, 4, 6 valence electrons here. 2, 4, 6, 8 valence electrons. So what we really need to do, we go back. What we really need to do is kind of, I say sometimes, throw the electrons in the middle here. So this actually would represent the double bond, as I just mentioned, right? Because there's 4 electrons. But let's count what we have now. 2, 4, 6, 8 electrons around this oxygen. 2, 4, 6, 8 electrons around that oxygen. So that would be a happy, stable way to look at this, because we have the octet achieved for oxygen that way, okay? So ultimately, though, the structural formula now would look like this, and it can be shown this way, but more often you're going to see those non-bonding electrons kind of shown on the edges too. Up next, example number 2, carbon dioxide. Now we have a singleton carbon. We have 2 oxygens. The vast majority of times, the singleton element is going to go in the middle, and that is true here. And as you recall from previous lessons, that carbon, and I'm going to show you, the Lewis structure for carbon. Carbon is very versatile because it does have 4 valence electrons, and it can bond quite easily with up to 4 different other elements. In this case, though, we have our oxygens. So let me do that. I'm going to kind of show it this way. So oxygen has 2, 4, 5, 6 valence electrons. The carbon has 4 valence electrons. And again, it seems logical to start this way, but it is problematic because we only have 2, 4, 6, 7 valence electrons around oxygen. That is not satisfied. The carbon has 2, 4, 5, 6 valence electrons, unsatisfied, and the same thing there. So no one's happy in this situation. So what I do again is I always suggest, let's kind of throw, especially non-bonding pairs of electrons, to the center. Oh, and then we have these two here. So let me do my carbon. I'll put my 4 valence electrons for carbon like that. I'll put my oxygen there. I'm going to bring in 2 of them there. 4, 6, 4, and 6. So we're maintaining the same number of valence electrons, the proper number, but depending on where they're located, you're going to be able to achieve an octet. So here we go. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. This works. This is great. And we get... Now, so this is a structural formula because it's using dashes. And this is what the molecular, ball and stick model would look like. Okay, I've got those 2 double bonds. This is a linear shaped molecule, and so is the oxygen. They're kind of straight lined, linear shape. Okay, let's move on. Okay, this third example is C2H4. It is named ethene, okay? And a quick look here. Anytime you have 2 carbon atoms, we're going to call it eth. And because this is a hydrocarbon compound that's only carbon and only hydrogen, it's part of the homologous series of hydrocarbons. This has a double bond. It's actually going to be ethene. All double bonded hydrocarbons are going to end in ene. Okay. Again, here is our carbon. 1, 2, 3, 4. Carbon. 1, 2, 3, 4. I only have 4 hydrogens. So I always, by the way, this is an important rule, always put any hydrogens you have on the farthest ends first, okay? Then I can put 2 hydrogens here, 1 there, 2 up there. It doesn't matter. I prefer to keep them on one side. So I will make those little dots there. Let me actually make them, okay? So of course, we have dissatisfied elements here, except for hydrogen. As a reminder, hydrogen is fully stable with 2 valence electrons because it's most like helium now. But if we look at carbon, we only have 2, 4, 6, 7 valence electrons and 7 there. It is unhappy. So we need to throw in our little electrons, okay? And then we end up with and I'll put my hydrogens around there, trying to be neat. So the hydrogens are still satisfied now, but notice each carbon. 2, 4, 6, 8 for that carbon, 2, 4, 6, 8 for that carbon, and we have a double bond, and we have an octet achieved, and let me draw it this way. Again, most commonly, you're going to kind of see the hydrogens go off on an angle like this, but they could go at a right angle, but this is pretty much more common. Ethene, the structural formula, and here it is actually, okay? Here's your ball and stick model for ethene. Okay, but in your homework you learned a little bit more about ethane, F-A-N-E. okay? The prefix represents the 2 carbons. You're referencing table P for that. ANE references alkanes. And alkanes all only have single bonds. Okay? And here was ethene and ethane. Double and single. Okay? By the way, I'll take this opportunity to introduce you. When you look at table Q, they have a column that's titled General Formula, CnH2n plus 2. I just don't want you to throw you off. But here's C to the N. That's 2 of them. H is 2 times 2 is 4, plus 2 gives you your H6. So this is actually pretty handy to use in your reference tables, because then you don't have to try to draw out the whole structural formula and electron dot formula to figure out if the molecular formula is in fact an alkene or an alkane. This is an alkane. Okay, so let me go on and introduce a triple bond for you. Okay, now a triple bond may involve 6 electrons that are being shared. These are covalent bonds. They're being shared, and there's 6 of them. So I'm going to give my example, C2H2. It is named ethine. And a quick look again. There's 2 carbons, eth. It's got the YNE. It's a triple bond. So it's ethine. It's an alkyne. Okay, and there's the general formula that you can figure out as well. So in this case, right, I'm just going, instead of making the messy version of this, I know I've got 3 bonds. So there's my 4 valence electrons for carbon. My other carbon, there's its 4 valence electrons. It's making the triple bond here. Always put your hydrogens at the very end. You have an octet for the carbons, and the hydrogens are satisfied with 2. And that is ethine. And here is your structural formula. Kind of cool looking, right? This is a very linear molecule with a triple bond between the carbons and 2 single bonds. So I can line these all up. Single, double, triple bonds. Ethane, ethene, ethine. Thank you. Hope you enjoyed. Bye.